Yeah, so if you are just joining us for the first time, if you've been following the class, you know where to download the questions, description below this video. And if you are just joining us for the first time, just download the questions I'm about to solve in the description below this video. There's a link there. Just download it from the link. So let's start with question 26. So question 26, they said the isomerization of cyclopropane to form propane is a first order reaction. So that's the first order reaction. At 760 Kelvin, 85% of a sample of cyclopropane changes to propane in 79 minutes. That means the initial concentration is 100%. As you all know, the initial concentration is always 100% because that's the initial. So it has to be the whole of it. Why at 760 Kelvin, 85% changed. That means the final concentration, since 85% changed, that means 85% was used, the remaining will be 15%. That's 100 minus 85. That's 15% in 79 minutes. And the time is in 79 minutes. Then they said, determine the rate constant. They're asking us to find the rate constant at 760 Kelvin. So since this is a first order reaction, the integrated rate we are going to use is ln B over B minus X is equal to KT. So we just have to fill in everything. And B is 100, that's 100 over 15 is equal to K times 79. And we'll solve for K. You see the board? I'll solve for K. So let me use my calculator. So let's just do that directly. That will be ln 100 over 15 all divided by 79. That will give us 2.4 times 10 raised to power minus 2 per minute or minute per. So this is the answer for question number 26, and that's that's option E. So that's the answer, option E. Question number 27, they said the isomerization of cyclopropane to propane follows first order kinetics. That means a first order reaction. At 700 Kelvin, the rate constant for this reaction, the rate constant is 6.2 6.2 times 10 raised per minus 4 minute per. And I said, how many minutes are required? And they're asking us for the time. How many minutes are required for 10% of a sample of cyclopropane to isomerize to propane? So for 10% they're asking us to find the time. So the initial concentration will be 100. The initial concentration is always 100%. Now the final concentration, what is the final concentration? They said 10% as isomerized. That means 10% of cyclopropane as isomerized. The final concentration will be 90%. That's just 100 minus 10. And so the final concentration is always the initial concentration minus what has been used. So what has been used is 10%. So it's going to be 90%. So let's solve for time. Since it's a first order reaction, we are still going to use this our formula equal to KT. So this will be ln B will be 100 over 90 equal to K is 6.2 times 10 raised to power minus 4 times T. So let's just do this. Let's just get this. This will be ln of this divided by this. So let me use my calculator to solve straight. That will be ln 190 all divided by 6.2 times 10 raised to power minus 4. That will give us 169 minutes. And that was option B. It's actually 169.9. 169.9 minutes. But in the option, it is 170 minutes. And you know, if you approximate this, you get 170 minutes. So the answer is option B, 170 minutes. Question 28. It said at 700 Kelvin, the rate constant for the following reaction, the rate constant K for the following reaction is 6.2 times 10 raised to power minus 4 minute per. How many minutes are required? They're asking us for the time. How many minutes are required for 20% of a sample of cyclopropane to isomerize to propene? So since 20% has been isomerized, the initial concentration is always 100%. The final concentration, since 20% has isomerized, the remaining will be 80%, right? And they're asking us for time. So we'll still use our normal first order, since it's first order. Right? Did they mention that it's a first order reaction? Okay, yeah, it's a first order reaction. Okay, here you see they didn't mention it's a first order reaction. They said the rate constant for the following reaction is this. How many minutes are required? Here they didn't mention it's a first order reaction, but how do you know if it's a first order or a second order reaction? If you look at the rate constant, the unit of the rate constant is minute per. I know for first order reaction, their unit, the unit of rate constant, this is the formula m1 minus n per time. For first order reaction, this will be m1 minus this order of reaction. Our first order is 1, that's 1. So this will be m raised to power 0 and t raised to power minus 1. And this t raised to power minus 1 can be per minute, can be in per second. So for a first order reaction, the unit will be always per minute or per second, stuff like that. That's to show you that it's a first order reaction. So in a question, they might not tell you that this is a first order reaction, but from the unit of the rate constant, you know if it's a first order, second order, third order, or blah blah blah, just like that. So since we found out that it is a first order reaction, then we use our normal formula in B over B minus X is equal to KT. Our K is 80. Let's just write it out. Ln B is 100 over B minus X is 80. A is 6.2 times 10 to the power minus 4. And they're asking us to find time. Then we solve for time directly. Let's see what we get. That's ln 100, 80, 6.2 times 10 raised to the power minus 4. That will give us 359.9 minutes. 359.9 minutes. That's 359.9 minutes. And from the option, our answer is option B, 360 minutes. If you approximate this, it's also 360 minutes. So question 29. It said a first order reaction has a rate constant of Here they've told us the first order reaction, so no need to worry. That's a rate constant of 7.5 times 10 raised to the power minus 3 per second. They're asking us for the time. The time required for the reaction to be 60% complete is, so that means the initial concentration is 100%, always 100%. Then the final concentration, initial concentration is 100%. The final concentration, since it is 60% complete, that means it is 40% incomplete. That means the remaining is 40% as the final concentration because 60% has been used. So it says you find the time. So as a first order reaction, now we're just going to use our normal formula B minus A equals to KT. Then plug in our values. B is 100 over B minus X is 40 equal to K. K is 7.5 times 10 raised to the power minus 3 times time. And if we solve for time, let's start. Here's my calculator. I'll be doing 100 or 40 all divided by 7.5 times 10 raised to power minus 3. That will give 122 minutes. Now 122 seconds, sorry. Our rate constant in seconds. So we need to get our value in seconds. That's 122.2 seconds. And from the options, that will be option D, 120 seconds. Because approximately this one is also 120 seconds. So 120 seconds. So when you solve in the exam, when you solve and you get something like this and you see your option 120, you don't have to get the answer like definitely because of all these stuffs can give a variability in the answers. So our answer is option D for question 29, 120 seconds. Question 30. The first order reaction, again, they gave the equation of this equation SO2 Cl2 giving SO2 plus Cl2. Those ones does not concern us. is 10% complete, and it is 10% complete, that means it is 90% remaining. Since it's 10% complete, 90% incomplete. In 80 minutes, that's the time. The time is 80 minutes. And I said, how long would it take? This is time for the first reaction. You can see that this is two scenarios. They said the first order reaction is 10% complete in 80 minutes. Then now goes, how long would it take for the reaction to be 95% complete? That means this is two scenarios in one question. Now I said, how long would it take? This is our first time. Time two. Then I said, how long would it take? This is what we're looking for. Would it take to be 95% complete? And for it to be 95% complete, it's going to be 5% incomplete. All right, this way. 5% incomplete. The initial condition is always 100%. So to find the time of this, we need to find the rate constant of the first scenario, and we put it into the rate constant of this of the second scenario. Then we find our time, because the rate constant is always constant. That's why it's a constant rate constant. So here our initial condition is 100%. So let's find the rate constant using our normal formula, integrated rate law. So B here is 100 over B minus X is 90. Is that 90? Yes, because it's 10% complete. Yeah. Equal to K. K is what? That we're looking for times time. 80. 80 minutes, right? So let's just look for K directly. So not waste a lot of time. Lean 100 divided by 90 all divided by 80. Rate constant will, so we got our rate constant to be 1.317 times 10 raised to power minus 3. Then since we've gotten our rate constant, now let's put it into the second scenario and get our time. So this is the data of the second scenario. So let's just plug this in and get our time. So we are still going to use the same formula. The same formula. This is the formula we're still going to be using. That will be lean. This one is always 100. Then b minus x is 5. Then k is what we got here. That was 1.317 times 10 to the power minus 3 times time. Then let's solve for time. That will be lean 100 5 all divided by 1.317 times 10 raised to the power minus 3. And that will give us 2,274.7 minutes. So option, the answer is option D, 2,300 minutes. When you approximate this, you just get 2,300 minutes. This is approximately 2,300 minutes. So our answer is option D. So question number 31. Benzoyl chloride. Let me check this stuff. Because when it goes off, I'm not able to hear me again. So benzoyl chloride reacts with water to form benzoic acid and hydrochloric acid. This first order reaction, that is the first order reaction, is 25% complete. Okay, it is 25% complete. That means it is 75% incomplete. This is the final concentration. Initial condition is 100%. It is 25% complete after 26 seconds. Giving us the time after 26 seconds. Then I said, how much longer would one have to wait in order to obtain 99% conversion of benzoyl chloride to benzoic acid? This is two scenario questions also, but it's linked to each other. They said, how much longer would one have to wait? That means this is T1. Now we have to find T2 before we even answer the question. So to find T2, like we want like question 30. So we need to find the rate constant first. So finding the rate constant, we use our formula B minus Bx. Okay, let me complete the data of the second scenario. They said how much longer would one have to wait in order to obtain 99% conversion. So to get 99% conversion, the final concentration will be 1%, right? Initial concentration is always 100%. So let's find the rate constant of this. That will be, let's input our values. B is 100, B minus X is 75. Then we're looking for K, that's our rate constant, and time is 26 seconds. So will be, K will be, let's solve for K. Now, lean 100, 75, all divided by 26 seconds. And that will give you 0.011. Let's just say 1.1 times 10 to the power minus 2. 1.1 times 10 raised to the power minus 2 per second, right? So we've gotten our rate constant. Now let's find our second time, the second scenario, the time for the second scenario. They said, how much longer would one have to wait in order to obtain 99% of benzoyl chloride? So let's find out. Also use this formula. Can you see the board? Okay, yeah. Also use this our formula. I'm not changing anything. I'm using the same formula. So B is 100 over B minus X is 1 is equal to K. This our K is 1.1 times 10 to the power minus 2 times time. Then our time will be, that will be lean 100, because 100 over 1 is 100. Lean 100 divided by 1.1 times 10 raised to the power minus 2. And that will give 418 seconds. 418 point, let's say 0.7 seconds approximately. But this is not our answer, because they said, if you look at the question, they said how much longer. That means compared to the first scenario, how much longer would I have to wait? That means they are comparing the second time with the first time. That means we've completed reaction one. We've completed reaction one. How much longer would I have to wait? And reaction one took 26 seconds, right? This one took 418 seconds. 480 seconds. That means how much time is between the space of this to this? You understand? How much longer would I have to be? That means how much time is within this to this? That will be 418. That will be T2 minus T1. That will be T2 minus T1. But this is T2. So that will be T2 minus T1. That means the time for the first reaction, the time for the second reaction minus the time for the first reaction. That's 418.7 minus 26. And that will give 418.7 minus 26. That will give 392.7 seconds. That's 392.7 seconds. And if you check from the option is actually option A. The question number 31, the answer is option A, 390 seconds. If I approximate this, 390 seconds. So question 32. A certain reaction A giving products. So this is the equation of the reaction. Is second order. This one is second order round. If this reaction is 10% complete after 20 seconds, how long would it take for the reaction to be 90% complete? This is also two scenario question. It says if this reaction is 10% complete after 20 seconds, how long will it take for the reaction to be 90% complete? So for the first scenario, the initial condition is always 100%. They said if it is 10% complete, that means it is 90% incomplete. 90% incomplete, right? After 20 seconds. After 20 seconds. I said, how long would it take? That means they're asking us for T2. How long would it take for the reaction to be 90% complete? And for it to be 90% complete, if it is 90% complete, that means it is 10% incomplete. So let's find for this. But you know that, so we have to find the rate constant for this. Then we use this rate constant to look for the time in the second scenario. But to do that, we need our integrated rate law. And for second order, it's different from first order, it's different from zero to order. For second order, it is 1 minus c minus x minus 1 over c minus 1 over c is equal to kt. So this is how it is in second order reaction. Or you can also write it like this. You can also write it like c minus x is power minus 1 minus c is power minus 1 is equal to kt. So let's use this information to look for the rate constant. So C minus X, okay, let's change this one to C. Let's not use B again because B is for first order. So let's just change this to C to understand better. So C minus X is 90 is power minus 1 minus C is 100 is minus 1 is equal to KT. We're looking for K and our time is 20 seconds. So 90, so let's do this with our calculator. 90 is power minus 1 minus 100 is power minus 1. This will give this will give 1 over 900. This will give 1 over 900 because of K times 20. I see the board. Yeah, so K will now be 1 over 900 times 20. We're going to divide both sides by 20. So our K will now be, I see the board. Okay. So our K will now be 1 divided by 900 times 20. That will give 5.6 times 10 to the power minus 5. 5.6 times 10 raised to the power minus 5. And our unit for rate constant of second order reaction is uh, I've forgotten, but let me do it as 1 minus 2, 2 minus 1. Have m is 1 minus 1, 2 minus 1. So this will be minus 1 per second. You can see I forgot the unit of the rate constant, but knowing this formula, you can get it. So we've gotten our rate constant. Now let's use to find the time for the second scenario. To find the time for the second scenario, let's change this up. Find the time for the second scenario. We're still going to use this formula: C minus X minus C raised to power minus 1 equal to KT. So C minus X is what? 10. 10 minus 100 raised to power minus 1 equal to K is what? 5.6 times 10 raised to power minus 5 times time. What's our time? Our time is what we're looking for. So I have 10 raised to power minus 1 minus 100 raised to power minus 100 raised to power 100 raised to power minus 1. This will give 9 over 100. This will give 9 over 100 because of 5.6 times 10 raised to power minus 5 times time. Then if you just divide by both sides, time will be 9 divided by 100 times 5.6 times 10 raised to power minus 5. And this will give 1,600 seconds. 1,607.1 seconds. And from the option, the answer is option B, 1,600 seconds. If I approximate, this is also 1,600 seconds. So that's for question number 32. So question number 33 is also testing our knowledge of second order reaction. So if I were you, I'll just solve the question. I'll solve number question 33 with what you've learned of me teaching you question number 32. So I'll just solve question number 33 to see if I really know what I'm learning or what you are watching. So you better solve question number 33 to confirm if you really understand what I'm teaching, what you are watching. But if you are lazy to solve that, or you solved it and you want to see the correction, let's go into question number 33. So he said a certain reaction, A giving products, A is giving products, is second order. If this reaction takes 85% complete in 12 minutes, how long will it take for reaction to be 50% complete? So let's just do this one very fast since I've explained how to do it. So it is 85% complete, that means it is 15% incomplete. The initial condition is always 100%. Time is 12 minutes. Time is 12 minutes. And so how long would it take? We'll come back to you later. So this will be using the formula C minus X equal to KT. So C minus X is what? 15. 15 is for minus 1 minus 100 is for minus 1 is equal to K. Is all we're looking for times 12. So K will be, let's just do this fast with our calculator. 15 raised to power minus 1 minus 100 raised to power minus 1 divided by 12. This will give 4.72. 4.72 times 10 raised to power minus 3 minutes. Is it a minute? Okay, minutes per. So we've gotten the rate constant. Let's find the time for the second scenario. Time for the second scenario. So for the second scenario, they said for the second scenario, they said how long will it take for it to be a 15% complete? So for it to be 15% complete, it's actually 85% incomplete. The initial is always 100%. Let's find out. Now we see minus x raised to minus 1, that's 85 raised to minus 1 minus 100 raised to minus 1 equal to k. This is our k. Now 4.72 times 10, let's clean this off, times 10 raised by minus 3, right? So by 72 times time. Let's just look for time direct. That'll be 85 raised by minus 1. I hope you understand what I'm teaching. I hope you understand because I've explained this in question number 32. So let's just go fast because of time and because of your data. 2 divided by 4.72 times 10 raised by minus 3. Minus 3. So this will give, how come it's 5 raised by minus 1? Right? Divided by 4.72 times 10 raised to power minus 3. I'll give, and this will give 22 seconds. 22 seconds. This will give 0.0.37 minutes. But if you look at the option is in seconds. So you need to convert this to seconds. So to convert minutes to seconds, just multiply by 60. If multiply by 60, we'll have 0.37 times 60. We'll have 22.2 seconds. 22.2 seconds. So our answer is actually 22 seconds. Option E. So 33 is option E. So question number 34. At 25 degrees Celsius, the second order reaction is 50% complete. That means it is 50% complete. Initial condition is 100%. It is 50% complete. That means it is 50% incomplete because it's 50%. 100 minus 50 is still 50. So 50% complete after 5.82 hours. After 5.82 hours, when the initial concentration of NOCl is this. So we got an initial concentration. Then I said, how long will it take for the reaction to be 75%? You can see here now, we have the initial concentration is 100%, and they also gave us the initial concentration as 4.46 mole per liter. But in this kind of question, just ignore the initial concentration. Ignore the 4.46 because they gave us the initial concentration of the 4, they gave it as 4.46, right? But they didn't give us the final concentration of mole per liter. Like they just give us 4.46. But here we can just use percentage to solve it because since we already know that it's 50% complete and we're going to 50% incomplete. So in this kind of question, just stick with solving it in the percentage way instead of doing 50% of 4.46. If you do 50% of 4.46, you will still get your answer, but it just take longer time. So just stick to solving it in the percentage way. So they now said, how long will it take for the reaction to be 75% complete? How long will it take to be 75% complete? I'm used to using B. Let me use C for the second order. It's not to cause confusion. So we want to look for a rate constant here, so we can apply it to that side. This will be C minus X raised by minus 1 minus C is equal to KT. So let's for rate constant. Then 50 minus 100 raised by minus 1 is equal to K. So we are looking for our time, 5.82 hours. 5.82 hours. So K will be, let me use my calculator. K will now be 50 raised to power minus 1 minus 100 raised to power minus 1 to divided by 5.8. And that will give 1.72 times 10 to the minus 3. 1.72 times 10 raised to power minus 3. So let's use this value of the rate constant to look for the value of the rate constant. Look for the time. Time for the second scenario. So they said, let's read. How long will it take for the reaction to be 75% complete? So for it to be 75% complete, it is actually 25% incomplete. The initial concentration is always 100%. They're asking us for the time. So we're still going to use this our normal formula. So here this is 25 raised per minus 1 minus c, that's 100 so minus 1 equals to k is what? This is our k. 1.72 times 10 raised per minus 3 times time. So time, let's solve for time. 25 raised per minus 1 minus 100 raised per minus 1 divided by 1.72 times 10 raised per minus 3. That will give, how come, 25 raised per minus 1 as 0.03 as 0.03 divided by 1 divided by 0.00172. I'll give us 17 hours. 17 hours. And 17.44 hours. So from the option, that will be option D, 17.5 hours. So question number 34, the answer is option D, 17.5 hours. So let's take a look at question number 35. This one is no solving question. It's just testing your knowledge and what you know. They said for the reaction x plus y given z, the reaction rate is found to depend only upon the concentration of x. A plot of 1 over x and 1 over the concentration of x versus time gives a straight line. What is the rate law for this reaction? So they want to look for we are finding they're asking us for the rate law of this reaction. So to get the rate law of this reaction, we need to know the order of the reaction, which is the first order, the second order, the third order. So for us to, when we've gotten the order of the reaction, then we can find the rate law. No, rate law is R, rate law is actually R is equal to K, then the concentration of A raised per N. So we need to find the order of this. We need to find this N to actually get the rate law. If you look at the graph is, we are plotting 1 over X, or plotting 1 over X, we are plotting it against time, right? And the graph is starting like this. Without me even knowing what to plot against what, looking at this picture of the graph, I already know it's second order. Why? Because second order reaction is the only one, is the only graph that is going upwards. Zeroth order, first order, their slope is always downward, but it's only second order that is going up and is not starting from the origin. So looking at the picture, I didn't know it's second order. But to explain further, how we know is in case let's say they didn't write, let's say they didn't put the graph now, and they say 1 over x against t. What is the order of the reaction? So to find that now, let's say they didn't give us the graph. So the answer is actually second order, but let's say they didn't give us the graph. We know from second order is actually one. This is the integrated rate law. 1 over c minus x minus 1 over c is equal to kt, right? But we want to restructure this formula in a way it's going to resemble equation of a straight line. So we can just take this 1 over c to the other side and get 1 over c minus x is equal to kt plus 1 over c, right? So let's say, so I want to compare this to the equation of a straight line. This y is equal to mx plus c, right? You can see that y is 1 over c minus x. That's the final concentration. And that's why the graph is 1 over x, final concentration. If you see, it said upon the concentration of x, that's 1 over c minus x. This concentration is actually final concentration. As you can see, c minus x. You can also represent this as c minus x or normal x, then put final concentration. Against x, x is actually time. As you can see, x is actually time. Then the slope of the graph is going to go upward. Why? Because of this. It's actually having a positive slope. Because it's positive, you don't need to put plus. So that's to show that it's actually having a positive slope. So that's why it's going upward. And the slope is actually k. Actually having a positive slope. So that's why we know that the answer is actually second order. So what's now the rate law? A said R is equal to kx raised power 1. That's first order. B said R is equal to kx raised power 2. a second order. So the answer is option B. C said R is equal to K X Y. If you look at that C, that's actually a rate law of a second order reaction. But overall, the actually second order because X plus Y, that's 1 plus 1 is actually second order. But here, they're only asking us for X, not for Y. Let's say it's X and Y. C would have been correct, but it's not correct because it's only X we are considering. So the answer is actually option B. Option D, rule that out. So the answer is our option B for question number 35. So they said question number 36 now. The reaction 2NO2 giving 2NO plus O2 is suspected to be second order in NO2. I'm saying they are telling us that it's a second order reaction considering NO2, only NO2. Now said which of the following kinetic plots, considering only NO2 like this now. Let me write the equation. 2NO2, 2NO2 giving 2NO, 2NO plus O2, right? Then they said it's suspected to be second order in NO2. So we are considering only NO2. We are considering only NO2. Which of the following kinetic plots would be the most useful to confirm whether or not the reaction is second order? So they're just asking us, they're asking us for the kinetic plot. That is what we are going to plot against what to give a straight line. That's the kinetic plot. So since it's a second order reaction, we know that we are going to plot the inverse of the concentration of NO2 from what I said earlier against that versus time to get a straight line. So let's look at that. Okay, our answer is even straightforward. So our answer is option A plot of NO2 is for minus 1 inverse is for minus 1 versus time. So that's option A. Question number 36 is actually option A. Yeah, so let's take a look at question number 37. It said the thermal decomposition of acetaldehyde is a second order reaction. Then he gave a following data and check your question. He gave a following data. They said you calculate the rate constant for the decomposition of the compound from the above data. So using that, we are just going to use this. We are going to use. We are just going to find the slope. Since they're asking us for the rate constant, I know in a second order reaction, the rate constant is k. In second order reaction, the rate constant is just k. So we're just going to be using this to find this. I know to find slope, slope is actually dy dx. That means, this is final concentration. This is final concentration. This is concentration time. Final concentration time. So I'm just going to be looking for d of one d of 1 over x over d of time. That's change in concentration over change in time. So that's what we're going to be looking for. So I'm just going to apply this principle into this question. So let's do that. That's k will be the change in concentration and change in concentration. Let's take from the final part. But here is in pressure, but pressure and concentration you can still use them interchangeably. So this will be 1 over this is 1 over 132 minus 1 over 364. 364. Let me clean this off. 1 over 132 minus 1 over 364. That's changing the concentration, changing the pressure. I'm taking the final pressure minus the initial pressure. That's changing the pressure. All over change in time. Time will be 720 minus 0. Let me do this with my calculator. Hope you can see the board clearly. Yes. This red marker is not very sharp. As 132 minus 1 64. That will be 4.82. This will give us 4.82. I'm coming, let me change this marker. So this will give 4.82 times 10, 4.82 times 10 is power minus 3 divided by 720. And our final answer will be 6.7, 6.7, can you see the board? Yes, 6.7 times 10 raised to power minus 6. Minus 6, then the pressure, that let's say that this will be the answer per second. So if you look at that, that's option D. So question number 37 is actually option D, 6.7 times 10 per minus 6 per millimeter mercury seconds. So this question, you can also substitute it as pressure. And I'll just give it the same unit. So that's option D. Question number 38. If you look at question number 38, is the continuation of question number 37. So instead of solving the first part, we're just going to use the answer we got from question number 37 to get out of question number 38. So question number 38, they gave us the same data and they're asking us, based on the data given, what is the half-life of the disappearance of acetaldehyde? So to get the half-life, the half-life of a second order reaction. This is a second order reaction. So the half-life of a second order reaction is actually 1 over Ck, where this C is initial concentration, right? This C is the initial concentration. This K is the rate constant. So we've gotten the rate constant to be 6.7 times 6 minus 6. That's question number 37. So I was going to apply this into this, and the initial concentration is going to be the initial pressure. That's 364. That will be 1 over 364 times the K will be, what's our K? K is 6.7. 6.7 times 10 raised per minus 6, right? So let's just solve this. This will be 1,364 times 6.7 times 10 raised to the power minus 6. And this will give us 410. That's 410 seconds. That's the half-life of that second order reaction is actually 410 seconds. And that's option B. So question number 38 is option B. So question number 39, they said for the chemical reaction A plus B giving C, a plot of concentration of A versus time is found to give a straight line with a negative slope. So since it's given a straight line with a negative slope, since it's given a negative slope, it can never be second order. It can be either zeroth order or first order. So zeroth order or first order, negative slope. It's found to give a straight line with a negative slope. What is the order of reaction? So, but they said it is a plot of the concentration of A versus time. You should know that that is zeroth order. The way if it was first order, it would be lean. Always on having lean, that's first order. But always on having the natural log of the concentration, that's first order. But if it's just ordinary concentration versus time, given a negative slope, that's zeroth order. And let me show you why that's true. The answer is zeroth order, question number 39. Let me explain further. So this is the integrated rate law for zeroth order. It's just final concentration minus initial concentration is equal to negative kT. Then we want to restructure this in a way it's going to resemble equation of a straight line. So that will be a final concentration is given minus kT plus the initial concentration, right? So this is just, we are just going to compare it to y is equal to mx plus c, the original equation of a straight line. So you can see y is AF as final concentration. The slope is minus k. The slope is minus k, and the x component of the graph is time. And so that's why it is this versus time, y versus x, concentration of A versus time, and the intercept is just this. So this is how we got to know that it is zeroth order reaction. So question number 40, for the chemical reaction A given C, no need to write. For the question of chemical reaction A given C, a plot of 1 over A, concentration of a plot of 1 over the concentration of A versus time was found to give a straight line with a positive slope. What is the order of reaction? As you add positive slope, just know that it's second order. Negative slope is for zeroth and first order, but the positive slope is always for second order. And they already said the inverse of concentration of A versus time. So that's second order. The answer is option C for question number 40. So for question number 41, they said the graphs below all refer to the same reaction. What is the order of this reaction? So you can see three graphs were given. One was like this, 1 over A time. Then this one went like this. Then this one was like this. This this is graph A. The graph B was like this. And graph C is something like this. Went like this, curved. And it said lean A versus time. So they gave us these three graphs and they asked, what is the order of this reaction? That means they're asking us what is the order. This is the graph that represents the reaction. Now, what's the order of this reaction? So, not to confuse yourself, to go straight to the point, because these three are actually the graph and they're actually correct. But you just go to the one that you're familiar with. Since these three represent the same order of the reaction, just go to the one you are familiar with. And the one you are familiar with is the one that gives a straight line. This curved line ones, we are not really familiar with those ones. So let's go to the one we are familiar with. And this is the straight line graph. You can see it's going in the negative direction, and that's a negative slope. And it can either be zeroth order or first order. But we are plotting the concentration of A versus time. So this one is not having a natural log, that means the zeroth order. Let's say it was lean A over time now. It's going to be first order. But it is ordinary the concentration of A versus time as zeroth order. So the answer is actually option A, zeroth order. So, question number 42. It said, for what other reaction does the half-life get longer? And the half-life is, they're asking us, does the half-life gets longer? And the half-life is increasing as the initial concentration, as the concentration, as the concentration increases also. Now it's asking us for what order is, as the initial concentration increases, the half-life also increases. So let's check. For first order reaction, for zeroth order, let's start with zeroth order. The half-life of zeroth order is A naught over 2k, right? That's initial concentration over 2 times the rate constant. This for first order. For second order, it is, so this was zeroth order, this was zeroth order. For first order, the half-life is ln 2 over k. This is rate constant. While for the second order, the half-life is 1 over concentration, initial concentration times rate constant. So looking at this, we can just get that you can see this, the half-life is directly proportional to the initial concentration here. Here, half-life does not depend on initial concentration, as you cannot see any concentration in this equation. That means half-life for the first order, half-life does not depend on concentration, on initial concentration. It does not even depend on concentration at all, the half-life, as you can see. The second order, the half-life, as half-life increases, the concentration decreases because they are inversely proportional. They are in a slant way, so they are inversely proportional. Let's say they are in a straight way like this, it will be directly proportional, but they are slanted, so it's inversely proportional. So for a second order, the half-life is inversely proportional. So as half-life increases, the concentration decreases. But the question says, as half-life increases, concentration increases, and that can only be found in zeroth order because they are directly proportional here. So as half-life increases, concentration also increases. So the answer is zeroth order. What you should take from this is for zeroth order reaction. Sorry, this is not first, this is zeroth. For zeroth order, this half-life is directly proportional to initial concentration. For first order, half-life does not depend on initial concentration. And for second order, half-life is inversely proportional to initial concentration. So let's go at question number 43. It said for a second order reaction, the half-life is equal to, you know that for a second order reaction, the half-life is actually 1 over Ck. Where this C is initial concentration. Just know that this C is representing initial concentration. They can write it as A naught, C naught, Ci. Just know that is initial concentration. So from the option given, the answer is actually option C, where they said the half-life is actually 1 over K A naught. Now from this zero, from this A naught, I see that they mean this is initial concentration. So that's the answer. Option A says 0.693 over K. That's first order into over K. B says Q over. Just rule that out. D says rule that out. E says E naught over 2K. That's zeroth order. So, but for the second order reaction, the answer is actually option C. So, number question 43, the answer is option C. So, question number 44, they said which one of the following changes would alter the rate constants for the reaction 2A plus B given product? So, without looking at the options, just know that the only thing that affects rate constant is temperature. Concentration does not affect rate constant, pressure does not affect. The only thing that affects rate constant is temperature. So option A says increasing the concentration of E. B says increasing the concentration of B. Concentration does not affect. C now said increasing the temperature. That's the answer. Temperature. D said measuring K and measuring the rate constant again after reaction has run for a while. The answer is actually option C, increasing the temperature. That's for question number 44. Answer is option C, increasing the temperature. So question number 45. Let's solve question number 45. So if you read this part of the video, make sure you subscribe and share this video to your other colleagues. So question number 45 is testing our knowledge on Arrhenius equation. So they said the Arrhenius equation, they gave us the Arrhenius equation. K is equal to A exponential minus acceleration energy over RT. This R is the gas constant, this is temperature. Now say the slope of a plot link K versus 1 over T is equal to, they're asking us for the slope. No, in a straight line graph, the slope, our slope is M. So they're asking us for slope. And I said they are asking for slope when you plot link K versus 1 over T. In fact, them giving us this stuff, they're giving us a bonus. Like giving us bonus. So let's just we want to like restructure this equation in a way that is going to resemble straight line equation. So once cancel this exponent, what are we going to do? We are going to take the natural log of both sides. Have a ln K is equal to ln A E exponential. This is this. So this is also ln K is equal to ln A plus the natural log of an exponent is going to cancel out each other. So that will be, this will be, it's now a plus minus E over RT, which is also minus rotation energy over RT. So since you are plotting link K, that means the link K, this is y axis, this is the x axis. So we need to bring this this old stuff, we need to bring it here and take this one back here. So that will be link K is equal to minus EA over RT plus ln A. Can you see the board? Yes. So we are going to just compare this equation to our equation of a straight line. Y is equal to mx plus c, where m is the slope, y-axis, x-axis, and this is the intercept. Yeah. So our slope is what we are looking for, m. So looking at it, this is y. M is going to be minus EA over R because our x, they already gave us x to be 1 over t. So if x is 1 over t, and this mx they are together, that means m will be minus EA over R. So the slope is actually minus EA over R. So, and the answer to that is option D. So question number 45 is option D. Question number 46, they ask what is the slope of an Arrhenius plot for the following equation. They give us the data. They said temperature. They gave us some values of temperature, 400, 500, then they gave us 600. Then they gave us the rate constant as 6.6 times 10 to the power minus 4. They gave us 2.9 times 10 to the power minus 1, and they gave us 16.3. Then they said we should find the slope of an Arrhenius plot. You know, from this equation, ln K is equal to minus EA over RT plus ln A. To find the to find the the slope, we you know that slope is any slope. To find the value of the slope is the y dx, or change in the y axis over change in the x axis. And from here, the y axis is actually ln k, right? That's change in ln k over the x axis. The x axis is also actually 1 over t. That's the x axis, 1 over t. So that's change in 1 over t, where t is temperature. So this is what we are going to be working with. We're going to be working with this. So you can just take two parts of the two parts of any of these. This is one, this two, this three. You can just take two parts of any of this data. So let's take 3 and 1. I like to take from the final information. So change in link K, that will be ln 16.3 minus ln 6.6 times 10 raised to power minus 4 all over change in the inverse. That was 1 over 600. The final 1 over 600 minus 1 over 400. Let's calculate that. So let's say ln 16.3 minus ln 6.6 times 10 raised to power minus 4 raised to power minus 4. That will be 10.11. 10.11 all over 1 over 600 minus 1 over 400. So 1 over 600 minus 1 over 400. That will give minus 8.33 times 10 raised to power minus 4. So if you calculate that, it's a 10.11 divided by, that will be minus 12136. That's the slope. So the slope is going to be minus 12136. So from the options, that will be option C, minus 122 times 10 to the power 4 Kelvin. So that's going to be our answer. That's going to be our answer to this. So we've got an answer. So for question number 46, the answer is option C. So let's check question number 47. It said the activation energy for the reaction, and I gave the equation, is 71 kilojoule per mole. How many times greater is the rate constant for this reaction at 170 degrees Celsius than at 150 degrees Celsius? So this is just comparing. There's a formula to this. And just give the formula. Show the formula is actually, it's also like Arrhenius equation, but they're comparing two scenarios together. So that this is the formula is log K2 over K1 is equal to 1 over this is 2 EA. Acquisition energy 2.303 R bracket T2 minus T1 over T2 times T1. Now coming. So they're asking us how many times greater is the rate constant for this reaction at 170 degrees Celsius. That means the reaction, the temperature increased from 150 to 170. They're now asking us how is the rate constant at 170? How much is it greater than 150 at when it was at 150 degrees Celsius? So one thing you need to know is the temperature must be in Kelvin. So temperature one is 150 degrees Celsius. Now 150 degrees Celsius plus 273. We have to get our answer in Kelvin. That's 150. 150 plus 273. That is 423 Kelvin. 423 Kelvin. The second temperature is 170 degrees Celsius. 170 degrees Celsius plus 273. So that one will give us 273. 443 Kelvin. 443 Kelvin. So you should also know that. And what you should also know is the activation energy should be in joule. It should be in joule per mole, not kilojoule per mole. So here they said it's 71 kilojoule per mole. So just multiply by 1000. That'll be 71,000 joule per mole. So let's just include this. That's log K2 over K1. Next report. Yeah, so log K2 over K1 is equal to our activation energy is 71,000 over 2.303. So our molar gas constant, you know that is just 8.314. 8.314 bracket. Difference in temperature 443 minus 423. That's 20. That's 20 divided by, then you multiply both of them. That's 423 times 443. That's a big huge number. 187 339 389 389. So let's do this as log K2 over K1, yeah, is equal to, so let's just solve this ones directly. As 1.303 times 8.314. Okay. So all this, when you calculate all this, everything like this, all we are going to get is 0.3958. So I'm just going to take the, so this will then be 10 raised to power 0.39. I'm just going to take the inverse of log of this one. As 10 to the power 0.3958. You get, that's what we shift log 0.3958, and that will give us 2.5. That will give us 2.5. Let me raise this. So that will give us, that means K2 over K1 is now 2.5. That means K2, the rate constant of the second scenario is 2.5 times greater than that of K1. So our answer there is 2.5, option C. So 47 is option C. Question 48 is also the same question. They just change the value. So they said if activation energy for a certain biological action is 50 kilojoule per mole, that will be 50,000 joule per mole. Let me see the code. It's too high. The activation energy is 50,000 joule per mole. 1,000 joule per mole. By what factor, how many times will the rate of this reaction increase? When body temperature increases by, it increases from 37 degrees Celsius, that's T1 is 37 degrees Celsius. We have to put it in Kelvin. And T2 is 40 degrees Celsius. That's when it is at fever. So they're asking us how K2 is greater than K1. By what factor is K2 greater than K1? It's just like what we did earlier. Let's calculate this. That's 7 plus 2 something. This one is 310 Kelvin. And this one is 313 Kelvin. So let us go into the formula. Let's plug K2 over K1 is equal to EA over 2.303R, or T2 minus T1 over T2 or T1. Then let's plug in our values. K1 is equal to, activation energy is 50,000 over 2.303. R is 8.314. You should know that R is a constant, so it's always 8.314. T2 minus T1, that's just 3. 3 over 10, 310 times 313, 97030, 97030. So let's solve all this. This is K2 over K1. because that was, let's just do this one. 1, 2, 3, 8.303, 303 minus 8.314, 970. So all this will give 0.0807. Then K2 over K1. K2 over K1, you now be, you take the inverse of log of this as 0.0. So this will give, let me write it up. Let me just clean this. Let's clean this also. So this will give K2 over K1 is equal to, that's 10 raised to power, sorry, let me see, log of 0.0807. That will give 1.2. Times K2 is 1.2 times greater than K1. And the answer is 1.2. So 48 is option B, 1.2. Question number 49. It said at 25 degrees Celsius, by what factor is the reaction rate increased by a catalyst that reduces the activation energy of the reaction by 1 kilojoule per mole? So this is also testing our knowledge on Arrhenius equation, but in a different format. This one is Arrhenius equation involving catalyst. This is not when it's involving temperature. It's not when it's involving catalyst. And there's a okay. They said they gave us temperature, but the temperature is just one. That means you're not going to be using change in temperature because there's not two temperature there. So this one is going to be changing the activation energy. And there's a formula to use. The formula is actually lean. Formula is lean K2 over K1 is equal to activation energy 1 minus activation energy 2 over RT. So this is the formula to use. In K2 over K1 is equal to activation energy for the first minus activation energy of the second over RT. So this is what to use. If you want to change this into log, you can just multiply by, so you can just divide this one by 2.303, so it will be log K2 over K1 is equal to EA1 minus EA2 over 2.303 RT. You know, any ln x, as I always say, ln x is equal to 2.303 log x. So you can just apply this to it. But let me just solve using ln to avoid too much numbers. So they now ask us by what factor is the reaction rate increased. So yeah, it's still the same thing you're asking us. How is K2 greater? By what factor is K2 greater than K1? So that will be ln K2 over K1 is equal to. Then they said the activation energy increased they say it reduces the activation energy of the reaction by, that means it's changed by, that means the change is 1 kilojoule per mole. As the change, it increased or it's reduced by, that means that's a change. If you say something is increased or something is reduced by something, that means that's a change between the two activation energy, and that's 1000 joule per mole. They gave us our information in kilojoule per mole, but we need to change it to joule per mole, 1000 joule per mole over R is a constant 8.314 times temperature. Temperature is 25 degrees Celsius. But no, we cannot leave it at 25 degrees Celsius. That will be 298 Kelvin. That means we just added 273. That's 25 plus 273. And that's 298 Kelvin. This will be lean K2 over K1 is equal to as 1000, 8.314 times 298. That will be 0.4036. Then I'll take the exponent of both sides. That will be K2, the exponent of a lane is a cancel out. Then I'll take the exponent of this. Then we'll do that. The exponent of 0.4036. That will be 0.4036. That will be 1.5. Can you see the board? Okay, let me write it up as as K2 over K1 is equal to 1.5. Times K2 is 1.5 times greater than K1. And when you bring this on here, so K2 is 1.5 times greater than K1, and that is option D. So question number 49, the answer is option D. So question number 50 is also the same format. They said at 30 degrees Celsius, the temperature is 30 degrees Celsius. Just know we are adding 273 to it. And that will just give us 303 Kelvin. Right? 303 Kelvin. And I said, by how much, at 30 degrees Celsius, by how much is the reaction's activation energy decreased by the addition of a catalyst if the catalyst triples the reaction rate? So for the catalyst to triple the reaction rate, that means K2 is 3 times K1. Now, because for it to triple the reaction rate, that means the rate constant of the second reaction is 3 times that of the first reaction. It's 3 times the rate constant of that of the first reaction because it's tripled. So they're not asking us to they're asking us by how much was the reaction activation energy decreased. That means they're asking us for EA1 minus EA2. This is what they're asking us, the change in the activation energy. That's what they're asking us. So let's write our formula down. Let's put this one. Let's say K2 is equal to 3K1. So our formula is ln K2 over K1 is equal to EA1 minus EA2 over RT. Don't forget that this is EA1 minus EA2, but this is K2 over K1. 1, 2, 1, 2. So this will be K2 is actually 3K1. So that was 3K1 over K1 is equal to, this is what they're asking us to look for, the change in activation energy. So just write down back over the rate constant is 8.314 times our temperature is 303 Kelvin. So this will be ln 3 because K1 will cancel K1. So what's ln 3? Ln 3 is actually 1.0986. That's 1.0986. Let's just put this one down back. Over 8.314 times 303. So our answer will just multiply, we cross multiply, then our answer will now be 1.0986 times 8.314 times 8.314 times 303. That will be 2767. 2767.5 joule per mole. But in the option, our options are given in kilojoule per mole. The only joule per mole there is 2.7 joule per mole, which is not correct. It's 2767 joule per mole. So we need to convert our joule per mole to kilojoule per mole, and we divide by 1000, as easy as that. So when we divide by 1000, we get 2 2.7 2.76, let's say 2.77 kilojoule per mole. 2.77 kilojoule per mole. And that's option A, 2.77 kilojoule per mole. So question 50 is option A.